In fact, our goal is to estimate f. And we know that we have all the tools for that. The statistical machinery there, all this knowledge on statistical methods are relevant and useful to estimate f. And we have basically two types of problems. F can take continuous values, and then we have the regression type of problem, or F can take discrete values such as 0, 1, or several categories, and then we have a classification problem. And once again, we have all the tools in the statistical package to address this question and to estimate F. But machine learning goes a little bit further, and in fact the distinction between statistical learning and machine learning is based on a subtle distinction on what we mean by learning. In fact, if the goal is to predict, then we may use tools that are very good at predicting, and we may focus on prediction accuracy. And then we may use machine learning tools, because this is the goal of machine learning, it's to predict. If the goal is to formalize a model, to learn and to explain why we observe this or that, then we may focus on statistical properties. And this is the goal of statistical learning. In practice, we use both of them to understand the data. You remember that at the beginning of this course, the right definition was we want to understand the data. All the tools and methods to understand the data are part of, depending on the author, these two categories. So far, we have also estimated F on the whole data set. And this is what I call the classical approach. So you have a data set, you estimate F on this data set, and we try to find the best fitting to the data set using some cost function, such as the MSE, for example, that I recall here, that is the minimum distance between what you estimate for F and what you observe for Y on the whole data set. This is what you have done all your life. Here, in this machine learning course and using the tools here, we're going to change this approach. In fact, if we estimate F on the whole data set and now someone gives us some new data, a new sample, some observation, and we want to predict, we will say, okay, well, we estimated well on our data set, we will probably be very good in your new sample. But we are not sure of that because we didn't do the exercise. And we will not know the type of error we are making in prediction because we have not really been predicting something. We have observed all the data and predict on the same data that we have estimated. Here is a change of paradigm. We will not use the whole dataset. We will use resampling. Since our goal is to evaluate the prediction accuracy of F on new, unseen dataset, we're going to construct a method, a way of working, so that we will always have somehow a way to assess that we are predicting well on new, unseen dataset. So for that, we will construct a new dataset. That is, instead of taking the whole dataset, we will take only one part. We call it the training dataset, where we will estimate F. And then we will use a validation set. On this validation set, we will predict using the estimate we have done on the training set, and we will compare to the value, because we have the true value on this validation set. We will be able to validate our prediction there. And that's a major difference, and this is how we will learn. We will learn by trying to minimize the error on the validation set. And somehow we will do some test and error procedure. And this is what learning means, by trying and error. And since the true value is observed on the validation set, it's part of the data you have at hand, you will be able to compute the mean square error, the true one, the one where you have the real value of y and its estimation. In fact, what is the problem? Why we do that? Well, if we estimate f on the whole data set, as we have seen, for example, with the KNN, we may have some overfitting. By trying to minimize the error, we may end up with a curve that is overfitting the data. In the extreme, it will be the curve that goes around all observation. And that's not good, because for a new observation, you will not really be good in predicting. So to avoid that, we will use this validation set. And this is where we will have a good evaluation of the prediction capability of a model and the predictor error on a new data set, unused for estimation. So this is the picture I showed you already. You have the training set and the validation set. And in practice, the prediction accuracy is evaluated only on the validation set. In practice, it's not a block like that. You will just draw randomly some observation and you will say, okay, I want to predict on this observation all over my sample, all over the dimension, all over the space. So I try to have a validation set that reflects the whole data set. So for that, it's better to take some randomly drawn observation all over and call that the validation set and not use that for the estimation. In fact, we shouldn't stop there. Since we have our data set, we can have separated into a training data set and a validation data set. But we can repeat that with many different training and validation sets, with M training and validation set. Here on this example, you see several of them, 8 of them, and for each line, you have a different training and validation set that are used. So what is the general method here? Well, you estimate f on the training set, you predict on the validation set, you see how well it works. Then you try on another set because you know that f will be good on your validation set, but what if I take another one? So you repeat that and you change, in fact, the validation set and the training set, and you repeat that many times, m times here. Why that? Somehow your prediction will be more robust if it's really good on average on any validation set you have chosen. And for that, you will in fact do what is called cross-validation or m-fold cross-validation that will estimate the accuracy of your prediction on not only one validation set, but on many validation sets, on M validation set. And you will select your model, the parameters of your model, for example, the K in the KNN procedure, in the KNN regression, on the basis of the average of the error you do on each validation set. Then instead of having only the mean square error for one set, you will compute this cross-validation error term here as the average of all the mean square error you have observed. And this is how you will try to find the best model, by trying to find the best model that minimizes this cross-validation error. So you can use this criteria to select or compare model or to compute and choose the right value for parameters in your models. For example, the number of neighbors in a KNN regression, or the number of polynomials in a polynomial regression, or the variable you should include in a multivariate regression and those that are not useful to include. So this cross-validation criteria is very useful and once again will be central in machine learning. How many M? Well, in practice, people tell you from 5 to 10. Too many of them could be quite demanding in terms of computation time and may not increase your performances. So we will stick to 5 to 10 folds 5 to 10 different validation and training sets. Since we are entering now in hardcore of machine learning, it's good to know what are the different tasks we have to perform in order to do machine learning. Several of these tasks may be time-consuming or demanding some CPU, some computing time for the machine. But here are several tasks. The first one is data collection, and we will not treat that here. It's somehow a prerequisite to work with machine learning, is to have data. We have also to organize them, and sometimes we have big data that are so huge that you have to reduce them to a dimension that is possibly handled on a computer. And this, once again, is a specific knowledge and specific tools that are not treated here. You also need to clean the data. We will not treat that here, even though we may see some methods that help you to understand some of the features in your data, and this can be part of the data cleaning. The 3 tasks here can be really long and time demanding, but are essential for a good machine learning project to work. There is a sentence that is very popular, that is trash in, trash out, meaning that if your data collection is not good or not well organized or not reduced in a good way or not cleaned well, there is no point that your machine learning project will provide you with good outcome. Then we will use also visualization. We will try to visualize in a good way what is the good model, what is a good fit, and we try to have some visual graphic that help us to decide either on the parameters to select or on the features of the machine learning project you are constructing. And of course, the data analysis that goes together with the data visualization. And this will be the core of this course. Data analysis, understand the data. Before I wrap up for this first module, I would love you to answer to these questions. So to wrap up this module entitled "You've seen that before," but maybe not all of that, I will just stress a few points. First, to understand the data, we probably need to go beyond linearity using some models such as polynomial or non-parametric models. And we have seen the example of KNN. We cannot believe that the world is linear, so we need to go beyond linearity. We also have seen that once we enter into non-linearity, we enter into the world of more complex model with more accuracy, but may introduce some variance in the estimation. And we will have this trade-off between a smooth model and a model with more variance. And this also can be transferred into being very accurate or being not so accurate, but more robust and probably being able to predict in a better way. This is called the bias-variance trade-off that we're going to see later on in many examples, but that we already have seen with the KNN. The theory that you may find help understanding what is going on. In the companion file that you will find on the learning management system, you will find a little bit of theory on the decomposition of the mean square error into bias versus variance. And you will understand that you cannot have both minimized at the same time. So the theory helps us understanding, but does not help us so much in choosing the right model. We will have to use empirical procedure, applied procedure, and define that for each case to choose the right model. The machine learning is really using the train plus validation set as a central framework for having a good accuracy, a good predicting behavior, and this is central in our approach here to use this train plus validation set separation. Again, you have seen most of that, or you'll probably be aware of all of these elements because you find that in any introductory course on machine learning. But it's particularly important, as we're going to see in the future modules.